Intanto grazie ancora a Vespignani, ho preso io personalmente un sacco di appunti, l'espressione che il computer è un macroscopio delle scienze sociali me la porterò dietro, mi fa vedere quello che uso tutti i giorni in un altro modo. E abbiamo chiuso parlando di Twitter e adesso l'ho anticipato prima Vespignani con Alan Mislove, anche lui della Northeastern University, College of Computer Information Science, andiamo a raccontare che cosa accade quando i dati sono i dati che vengono dai social media. Alan Mislove, prego.
Okay. Grazie. Can you hear me? I guess so. So I'm going to start by saying that unfortunately I'm going to have to speak in English. I don't speak Italian, so I apologize to those of you who do not speak English. But I'd also like to begin by thanking the organizers of the conference for the invitation to this beautiful city as well as to this very exciting workshop. So, okay. So before I really get into the talk, I'd like to spend a couple of minutes to describe my background, my interest, and sort of what my perspective is on big data. As the introduction said, I am currently an assistant professor in the College of Computer Science at Northeastern, and my background is actually in computer systems. I did my Ph.D. building peer-to-peer systems, very technical work and so forth. And lately, my group has been looking at leveraging information from online social media to help build systems. So we're still looking at very technical issues, but we're looking at trying to use the big data, use the new web and whatnot to build better systems. And so my goal in this talk is really to convince you that if you're a systems designer, you should be considering these issues as well. And so what I really want to do is begin by sort of giving you a motivating example for why systems designers, which traditionally we like to ignore users. They're messy, they're dirty, we like our protocols, we like our computers, right? And so we can't really do that anymore. So let me give you an example for why. So what I want to do is consider online social media as an information sharing system. It's a way that users can exchange information. So in order to sort of understand what's new here, what I like to do is to compare the online social media to the previous popular information sharing system, which I'm going to determine to call the web, classic web, or the web 1.0, the web before Facebook. Okay? So let's look at how that was organized and how we located information. So, for example, let's take a look at the web here. The web is a collection of web pages, and each web page links to other web pages, like so. And what we've seen is that this results in a graph, and this graph has a number of useful properties. For example, if you look at the graph, you can follow the links and find out what the important pages are. This is exactly what Google does, and it says, aha, the page there shown in red has lots of incoming links, and therefore it's an important page. Right? This enables us to sort of understand the system as well as use it in our daily life. But let's take a look now and look at what happens in online social media. Well, first off, the content that's shared in online social media is not web pages. Instead, it's content like photos, videos, status updates, blogs, and so forth. And in particular, that type of content doesn't link to other types of content in the same way as web pages do. Right? Think of like a Facebook photo. A Facebook photo does not link to another Facebook photo in the same way that a web page links to other web pages. Instead, what the photos link to are users, right? Users who uploaded the photo, users who comment on the photo, users who appear in the photo, and so forth. And so what you see is that the network is no longer simply a content network. Users are a first-class entity in our system. But more importantly, what's holding this together is literally the social network. Our information system now has users embedded in it and is based on the structure of the social network. And so we as systems designers have to look at the social network. We have to consider the users and the social connections that exist if we want to build tools that are able to use these sorts of networks. Now, for example, this is one of the reasons why search on online social media is not nearly as good as search in the classic web. Because we understand how the web graph works, but we don't necessarily understand many of the properties of this graph. So, my group's research is really trying to do that. We're trying to leverage properties of online social media and then use that to build better systems. Now, to do that requires two steps. The first is we need to be able to understand what are the relevant properties, right? What properties of social media exist and how can we use those in systems? And the second is to actually build systems and algorithms that are able to do that, that are solve existing challenges and basically just build better systems. And so what I really want to do in this talk is give you two examples of the types of problems and challenges that we're interested in and that we're sort of actively working on, to give you a flavor of why I think this is such an important area. So for the rest of the talk, what I'm going to do is talk about two trends, things that are different in the online social media space than the previous systems, and how that's requiring us to take new approaches to dealing with lots of these problems. And so the first of these two trends that I'm going to talk about is the changing patterns of content creation and exchange. Now, what I mean by that is the ways that content is being created and the ways that content is being exchanged between users is very different in online social media than in Web 1.0. And we need to think about how we architect our system to take this into account. So, let me start by again considering the pre-2005 web. This is Web 1.0, web before Facebook. I'll say 2005-ish, but this is sort of just the classic web. So what I've shown on the slide is sort of a high-level, imagination of the internet. You've got internet service providers like Telecom Italia and so forth. They link up, and then you've got end users who also connect to this network. Now, in the classic web, the way it worked was there were popular websites. For example, La Repubblica, New York Times, and so forth. The way that it worked was users who had web browsers would access data by sending a request to La Repubblica to be transmitted across the internet, across the various ISPs, and then the data would eventually be received. Now, as systems designers, one of the things we did is we looked at this and said, well, aha, we're sending the data multiple times over the same links. This is wasteful. This costs La Repubblica money, this costs the ISPs money, and it's wasting resources. So instead, companies like Akamai said, okay, let's put some servers in the ISP, let's put some web caches and so forth. And then what we can do is when users request the content, instead of going all the way across the internet, they just go to this local server. This worked great. Akamai is a multi-billion-dollar company, and everybody's happy. But this is true for the Web 1.0. And now I want to talk about Web 2.0. And I'm going to argue that there are two fundamental changes to the way Web 2.0 works that makes this approach not work so well. The first of these two changes is a change in the content popularity distribution. Okay? So the way I'm going to explain this is by this graph. Now, this graph is actually very easy to understand. Along the x-axis, I've put all of the documents ranked from the most popular to the least popular. So most popular on the left to the least popular on the right. On the y-axis, I've put the cumulative sort of popularity of those documents. So the way to read this is to say, like, for example, that green point means that the top 10% of the documents receive 40% of the hits. Okay? And this explains why web caching works. If you cache the 10%, you get a huge fraction of the hits. Okay? So, in particular, if we look at the x equal y line, that represents a perfectly even distribution. The top 10% of the documents get 10% of the hits. The top 20% get 20%. Okay? So now let's take a look at what this looks like in the classic web. What we see is a distribution that looks something like this. It's biased. There are very popular documents that get lots of hits, and there's a whole bunch of documents that get very few hits, right? And in general, you design your web cache to cache these guys. And the actual shape of the curve varies a little bit depending on which website you're seeing, but in general, they all follow this same trend. Now let's take a look at, for example, Facebook photos, an example of Web 2.0 content. What you see is something like this. This is a study we did of photos on Facebook. Now you'll notice that this is much closer to a perfectly even distribution. In particular, there aren't nearly as many hits that exist in this distribution, and it's very different than the Web 1.0 distributions. So what's the implication of this? Well, what you're seeing is that objects have much more narrow scope. Photos on Facebook, there isn't a photo on Facebook that's as popular, relatively, as the New York Times or La Repubblica. Things are much more locally scoped and are of interest to a smaller number of users. And so what this means is that in the classic web, we were able to use caching. We cache 10% of the documents, and we can get 55 to 95% of the hits. But in Web 2.0, we can't do that anymore. In particular, with those Facebook photos, we cache 10% of the documents, we only get 27% of the hits. Right? So it's much more expensive, and we need to look for new techniques to be able to distribute this content. Now, the second of the two changes that I want to talk about is a change to the way that content is being generated. Right? So let's look at the web. Let's look at my sort of imaginary graph here. And the way it works at sort of a protocol level is very similar. Instead of La Repubblica, our popular website is Facebook. And again, users request data by sending a message to Facebook and so forth. But the difference is that the data you're downloading, like for example, the photos you go to view on Facebook, were originally uploaded by somebody else. They weren't generated by Facebook. None of the data on Facebook is actually generated by Facebook. Instead, what we're essentially doing is taking a photo, sending it to Facebook, and then Facebook sends it back, right? And this is even though we know there's a strong geographic correlation between people who generate photos and people who view photos. For example, if you live in Turin, your friends probably live in Turin, they're interested in your photos. And yet we're sending those photos all the way across the internet to California and back, twice for every view, right? As a computer scientist, this is somewhat offensive, and we need to look for better ways to be able to do this, right? So to sort of summarize this, what we're seeing is a change in the workload, right? That there's significant content creation happening at the edge of the network by the end users. And this is due to a number of trends, this online social networks, but also the popularity of digital cameras, digital camcorders, smartphones, and so forth. So in other words, individual users are now empowered to generate significant amounts of digital content. So what we're seeing is that there's a transition. That in the classic web, the workload was from the center. It was generated by the large media organizations and distributed to the edge. Whereas in Web 2.0, what we're seeing is a workload that's from the edge to the edge, from users to other users. And the problem is that we're still delivering it using Web 1.0 architectures, techniques like web caching, techniques like content distribution networks, and so forth. And this represents a mismatch between the infrastructure we're using to distribute a workload and the workload itself. And the result is that it costs everybody else extra money, right? That, for example, sending everything to Facebook requires sending it across the internet twice. And this is in spite of the fact that the distribution of photos on Facebook is quite possibly the most naturally decentralized workload you can possibly imagine. I'm sharing with people who are around me, and yet we're sending it all the way across the internet. So what we're interested in is trying to build a system that can decentralize content delivery over the web. In other words, to try to build a system that is designed for the types of workloads we're seeing driven by this sort of big data and online social media trends. Now, if you're familiar with the way the web works, there's a lot of technical challenges here. I'm not going to go into these too much. But the basic problem is that the web is fundamentally client-server. You have web servers like Facebook. You have web clients, which are your browser, right? And to turn a web browser, to have it help distribute content to others, in other words, to have you be able to give your photo, for example, to Alessandro, requires a lot of technical challenges, especially if you don't want to make any changes on the end hosts. But that's exactly what we did. And essentially, we have a system called a web cloud. And the way it works is that if you run a website, you run our software, two people come to your website, the first one asks for a photo, you give it to them. But then the second one asks for the same photo, you tell the second to get it from the first, right? Due to the geographic proximity between users, this keeps it local to the internet service provider. It saves you money because you don't have to distribute the content, and it's basically an architecture that more closely matches the workload. And now I'm going to show you that not only does this sort of look better from a computer science perspective, it also saves everybody money. So what we've done is we got the Akamai logs. Akamai is a big content distribution network from one of the top 50 sites that's an online social media site in the United States. And so what I'm presenting on the graph here is their instantaneous bandwidth. Okay? Along the x-axis is 1 week's worth of time. On the y-axis, how much bandwidth they're using to distribute content. Okay? It's a US-centric site, so you see these very nicely diurnal patterns. Now, if you applied web cloud to this, in other words, in their site, when one user requests an object, if somebody else is online, they get it from them, you'll see that the amount of bandwidth they have to spend goes down dramatically. And in particular, their costs, which are often determined by 95th percentile bandwidth, drop by 76%. Because we've designed an architecture that much more closely matches the workload. So I'm not going to go into a technical discussion. Please feel free to ask me after the talk. I'll be around. But to summarize this part of the talk, we were motivated by the trend that there's a shift in the patterns of content creation and exchange. And yet today, we're still using old architectures for distributing Web 2.0 content that don't match. And so we built a system that's able to decentralize web content delivery, allow users to distribute content themselves to their friends. And this results in a savings as well as a more scalable system. So that's all I want to talk about for that topic. Now I want to switch gears and talk about the second trend that we're looking at. The first trend was really concerning a system design. How do we build our network to be more scalable? The second one is concerning security. How do we build our systems to be more secure? And the trend that's motivating us here is that there's a changing notion of accounts and identity in Web 2.0 systems. And let me explain exactly what I mean by that. So think of user accounts in systems. Now, these are so ubiquitous these days that we don't even think about it. But essentially what an account represents is a group of privileges that are associated with one user or a group of users or some entity, right? Now, traditionally, these accounts were verified by service operators. For example, like your email account at your workplace, you probably went, you showed them your ID, and then they gave you your account. But the trend is that on sites like Facebook, sites like Gmail, Dig, TripAdvisor, and so forth, accounts are free. All you need is an email address, right? And what's worse is that these accounts that are free come with privileges. For example, on Facebook, I'm allowed to message people. On Gmail, I'm allowed to store data. On sites like Dig, I'm allowed to vote and whatnot. So what the result is, we're seeing attacks that are called Sybil attacks. What this means is that one user creates a huge number of accounts on some system because the accounts are free, and then uses that to attack the system in some way. Now, this isn't just a theoretical attack. There have been studies that have found this happening in peer-to-peer systems, in voting systems like Dig, where spam is voted to the front page, in systems like TripAdvisor, which are review sites, where very bad restaurants get voted very highly because the user creates many accounts and votes and so forth. Right? So this is a real attack, and it's getting worse because we're seeing more and more of these systems with free accounts. So what I want to do is describe sort of our approach to dealing with this, and I'm going to narrow my scope slightly and say that what we're going to do is focus on how this is affecting online marketplaces. These are sites like eBay, Overstock Auctions, and Amazon.com Marketplace. What I mean by this is these are sites where users can list individual items for sale, and then other users can buy them. Okay? And these are very successful websites. For example, eBay alone sold $62 billion worth of goods last year. So there's a huge amount of money being transacted on sites like this. So what I'm going to show you first is how they're subject to Sybil attacks, how users who can create multiple accounts can steal money in these systems. So how many of you have used eBay? Probably most people, a good number. So the question is, well, how do you determine if the guy who you're going to buy something from is fraudulent or not? What you do is you look at his feedback, right? So every user has a feedback profile, which simply lists, when I buy something from you, I'm allowed to vote and say whether I'm happy with the transaction, whether I'm unhappy. And so it looks something like this, where the red user has lots of positive feedback, whereas the blue user on the right has both positive and negative feedback. So if you're a buyer, you're going to pay more to buy something from the red user than from the blue user. Okay? So having a positive reputation is good. But here's the trick, which is, let's suppose you're malicious and you want to get a positive reputation, but you don't want to go through the work of actually selling good, real stuff. What you do is you create a bunch of fake accounts, and then you list items with one of your accounts and you buy it with the other. Right? You pay a small transaction fee to eBay, but then you get to provide yourself with good feedback. Right? And so what you see is something like this, where now the red user looks like he has an even better reputation. Now, this isn't just a theoretical attack. We've seen this happen. And recently there was a guy arrested in Miami who had stolen over $700,000 from 5,000 users by using over 250 accounts. He would link them up, make them all look good, and then list items with a good reputation to real users and take their money and run. Right? And this is very hard for eBay to detect because eBay doesn't know, and you as a user don't know, that these red users are all actually owned by the same person. They have different names, they look different, they might sell different types of items. So the question is, what do we do? So we built a system that we call Bazaar, which is looking at trying to strengthen user reputations against the fact that you can have multiple identities and multiple accounts. And there's basically two approaches you can take when you're working on this problem. The first is you can use what are called machine learning techniques, where essentially you say, aha, well, there's certain properties of malicious users. For example, they tend to make networks that look like this. And you can go and try to detect where those exist. But the problem with that approach is that you're in an arms race. You're building a detector, And when you build it and deploy it, the attacker will get stronger. He'll obfuscate his abilities, his actions even more. You have to build a better detector. He gets stronger. And you never win. It's sort of like the spam problem, where you're just continually fighting. So what we did instead is we built a system that strictly bounds the amount of fraud that the users are able to conduct. But it assumes the same exact model of today, meaning accounts are still free, because eBay isn't going to require users to show a passport, for example, to get an account. So let me explain briefly how it works, which is Bazaar is based on the insight that transactions between users in online marketplace represent shared risk. If you're the seller, if you're the buyer, you're risking that when you pay your money, you're never going to get your item. So you're putting money on the line. But the seller is also putting his reputation on the line, because when he sells something to you, you now get to vote on him. And so you could provide negative feedback. So what Bazaar does is we sort of generalize this to form something called a risk network, which is actually very simple. The way it works is if I buy something from you on a site like eBay, and I'm happy, you and I have a link. And that link is weighted by the amount of the transaction. Okay? So you simply get a graph that connects the identities by the amount of successfully rewarded risk, meaning how many times was it successful. And you can build this from the feedback system of today. So the question is, now that we've built this risk network, how do we actually prevent fraud? Let me show you. So let's suppose that we have a buyer and a seller who are about to complete a transaction. The buyer is about to click purchase. What Bazaar does is it looks at the risk network and says whether or not it thinks that the transaction is fraudulent. The way it does that is by calculating something called the max flow in the risk network. If you're not familiar with max flow, essentially what it means is we imagine that these are pipes with certain capacity, and the question is how much flow could the buyer push to the seller through all the paths in the risk network. So in this example, what we'll see is that the buyer has a bunch of links, for example, a $100 link and so forth. But there's a bottleneck in the network. In particular, that seller's $5 link. So it says despite all the links the buyer has, he can only push $5 worth of flow to the seller. So the max flow is $5. Essentially, it's what's the minimum cut that exists between the buyer and the seller. So well, I'm going to show you now that if you do this and you compare the value of the max flow to the transaction value, then you can detect fraud. So in particular, what Bazaar does is says if the max flow is less than the value of the transaction, it's declared as fraudulent. And let me show you why this works. So let's suppose that our seller was malicious, and he did exactly what we saw before, created fake accounts, list items with one, bought it with the other, gave himself positive feedback. What would that look like from a network perspective? What it would look like is this, where there's links off to the side. Now you'll remember that eBay doesn't know who's owned by the same user, but it does see it from a network perspective. In particular, these links don't increase his max flow. He's still got that $5 bottleneck. And in particular, he can create a whole fake network over here, and again, it doesn't increase his max flow in any way. The only way to actually get more max flow is to participate in real transactions with real users, meaning he has to be good. So I'm not going to go into a more technical discussion there. Again, feel free to ask me after the talk. But I just want to sort of give you a feel for the sorts of problems we're interested in, the trends that are changing, the assumptions that we make as system designers, and how we're trying to respond to those assumptions. So to summarize this part of the talk, in Bazaar, we were looking at the trend where accounts are now free. This can result in reputation manipulation. But we built this system, simulated on data from eBay, and we found that it would have prevented lots of fraud, and it very rarely impacts honest users. So with that, I want to thank you all for your attention. Thanks for coming. Again, thanks for the invitation to this conference. Again, the sorts of research that we're interested in is looking at the increasing integration of our social systems and our computer systems, and arguing that we as computer designers, who are typically very engineering-centric researchers, really need to consider the sorts of systems, or sorry, the opportunities and challenges that these systems are presenting. So thank you very much. And